Hello, everyone. We want to welcome you to the next iteration of going through the deep learning textbook. So for people that hadn't joined us before, these are bi-weekly broadcasts, basically, where we're allowing people to kind of tune in, create a discussion and ask questions. Each week we have a presenter that's going to go through a specific chapter of the book. And we'll give kind of a brief intro of what the material that was covered in the chapter. They're also going to help answer any questions from people that are watching. And this is, of course, to help create a larger community around deep and AI and help, educate people and hopefully further people's understanding and knowledge of artificial intelligence. So I want to introduce our volunteer presenter this week. We have Alex Shim, who is a research consultant and a mathematician. So he has volunteered to cover chapter 3 for us today. So we're really excited to have him on air with us. Do you want to say hi, Alex?
Hi everyone.
Wonderful. I'm going to go ahead and put your screen as the main screen here, and then so you've already got screen sharing going, and then you can go ahead and introduce the chapter and what you'll be covering and start going through the slides.
Okay, that sounds great. All right.
Okay, go ahead.
Okay, hello everyone. I'm Alex Shim, and as Laura mentioned, I'm a research consultant and I guess a mathematician. I studied mathematics at Caltech, and I was interested in presenting this chapter because, well, people cover probability theory a lot, but there's a lot of extra background into it, which is required to set it up. And it's harder to find someone who can discuss that. So I wanted to also lay out some of the background behind it as well. And that includes introducing some more advanced mathematical concepts. And sometimes you'll see those when you read research papers on deep learning as well. And hopefully this will give people some understanding into that as well. And also providing this information, it might help your intuition a little. It might adjust how you think about probability a little. And with that said, let me move into the lecture. First of all, why are we concerned about probability, not in general, but for deep learning in particular? And mainly it's because that when we evaluate models, we are basically trying to create functions and we're trying to fit them to certain situations. And in order to evaluate the models, we usually have a loss function, which we'll talk about, I think, later in chapter 6, I believe. And in order to evaluate the loss function, you have to take some sort of average loss over the entire data distribution. And usually that's done with expected values, and expected values are dependent upon the probability distribution of the data itself. And so all that is implicitly going into this, into the idea of our expected values and our loss functions. And it's something that's assumed, but it's really important, because thinking about that and thinking about how our data sampling allows us to approximate our expected value, that's pretty much how we do gradient descent, and that's how we do parameter updates, and it's how we optimize our models. And more generally, probability allows us to so in science, there's a lot of deterministic systems. That is, you have some sort of fixed input and you have some fixed output. But in many cases, there are non-deterministic systems, which we call stochastic systems, and it introduces randomness in the system. So there could be multiple possible values, and you have to figure out the probability for each possibility. And some of the ways the stochastic systems can manifest themselves is through inherently stochastic systems, where it's sort of built into it, sort of like in quantum physics. There's when you try to predict where a particle is, that it's not going to be in a set location. It's going to cover a probability distribution. And also in science, you could also interpret it as limitations in measurement, and also the incompleteness of the model. And that is to say that we have a lot of theories, but sometimes they're not they won't always be exact. There might be some friction or noise or some things that we haven't accounted for, and that can introduce some sort of random error into it as well. And let me just check really quickly to, sorry, I want to check. Also, I will be trying to look at the chat as well.
Yep, I'm actually following the chat, Alex. So if there are any questions, so if you want to focus on the presentation, I can,
Okay.
help also with that. Yeah, not a problem.
Okay. And let me go on. And this is something that they talk about, and it's more philosophical, so I don't want to get into it too much, but there are different interpretations of probability. When somebody says the probability of something is this value, it's not always clear what that means. And there's actually different ways you can interpret it. And the first one was actually the more classical interpretation. I believe there is a mathematician who's trying to figure out. Some gambler went up to him and asked him, "How do you determine what are the odds for what are the best odds for whatever situation?" And he did that by in some, for example, if you're rolling a dice. If you're rolling a die, then there are 6 possible outcomes, and if you assume that each of these outcomes is equally possible, what's a possibility? What's a probability that you land on an even-sided die? And to do that, you would count the number of. You would assume that each die would have an equal probability. So you count up the number of even outcomes and you divide by the total number of outcomes. And more generally. And that's sort of limited because sometimes the probabilities are not going to be even. For example, you might have a weighted die, which is like weighted towards some faces as opposed to other faces. Also, in sort of as an extension of this, in science, there's what's called the frequentist interpretation of probability, and that's sort of more an empirical observation. That is, it's a long-term average. If I flip a fair coin like infinitely many times, then half the times it'll come up heads and half the times it'll come up tails. And that probably is based off this idea that some sort of long-term averaging of events. And there's also the measure of belief / Bayesian interpretation. And in that, you're going. So in the frequentist interpretation, you remove a priori assumptions, but for the Bayesian interpretation, you might say, like, given that you might add in some previous knowledge about the system and then use that in order to influence your idea of what probability is. I'm sorry, it's not very exact. But I'll be focusing more on the axiomatic approach, which is a more mathematical formulation of what probability is through mathematical structures. And if you just focus on an axiomatic approach, then you don't really worry about, well, what the interpretation is. As long as it fits your definition of what probability is, then you can go along with it. And I'm sure in the real world there's philosophical debates like, are you a frequentist, are you a Bayesian? But we're not going to talk about that. Okay. Now, in this chapter, for Ian Goodfellow's Deep Learning book chapter, he covers a lot of basic concepts of probability, and these are probably the most important and fundamental concepts, and we'll be covering them as well. And I'll be covering a lot of information, but if you're the ones that you'll use the most are these, and it'll be random variables, random vector spaces, expected values, probability distributions and densities, conditional probability, and Bayes' rule, and later on information theory. And these, this will be, you don't have to remember everything that I say, and I'm sure most of you are actually probably pretty familiar with some of these concepts as well. So if you're getting overwhelmed, then don't worry about it too much, because as long as you remember the more the key concepts, then in most cases you should be okay.
Yes. Oh, and
And let
Alex,
me,
also,
sure.
Alex did share the slides as well on our meetup page. So if you are interested in following along online, those are available. And of course, you can always watch the video again if there's anything you don't understand and you'd like to review it. Feel free to just watch it over again, and then you'll have a better understanding.
Mm-hmm. Absolutely.
Yep. Mhm.
Okay. And there's a link on the meetup page, and I think we can share that as well in the live chat, I believe. I shared it on
Yes, let me
Google
do that.
Documents. Yeah.
Yeah, I'll go ahead and share it now.
And so I'm going to move in. So I'm going to be talking about a lot of generalizations of probability, but let me first start out with our more ideal situation, and that is that usually we're working with we're going to be working on the real line. Our set is going to be the real line, and we're going to be defining our measurable sets as intervals. So it'll be open intervals, closed intervals, intervals that start closed on the left side and are open on the right side, and vice versa. And these are what we call measurable. Um, these are what we'll define as our measurable sets. And our probability function is going to be defined on all measurable sets. And and it will look a lot like an integration. For example, if we have it, well, in these situations, what we might have some probability density function like p of x, and in order to evaluate the probability over an interval from a to b, we'll just integrate it from a to b, and that's
Hey,
all right.
Alex,
Sure.
so for people that might not be as familiar with mathematics, can you describe what an interval is in general? So to give them like an image in their mind.
Okay. Well, I wish I had some picture. Well, so if you imagine the real line, um, in, well, so an interval from 1 to 2 will contain all the numbers between 1 and 2. So 1 will be sort of the left side of it, and 2 will be the right side of it. For an open interval, it will not contain the endpoint of 1. And for a closed interval, it will contain the endpoint of 1.
Perfect.
So in closed intervals are inclusive, open intervals are not inclusive, and there's some topological importance of that difference.
Mm-hmm.
Um, and we might sort of get into that when we briefly discuss topology. Um, but this is but but this is sort of our ideal situation because the real line, it has a lot of nice properties. Like we have a very clear idea of what distance is. We know how far. Um, it's something called a vector space, which if I guess I'll talk about that maybe a little bit later.
Sure.
But it's very ideal, and in most cases, we might mention a few very strange situations,
Mm-hmm.
but in most cases, our expected values, it's going to be like a Gaussian distribution over the real line, or it might be a uniform distribution that is like the probability is equal over from, let's say, from 0 to 1. So it'll usually be much nicer.
Sure.
So
And can you explain what a Gaussian distribution is, please?
okay. Well, it's something called, well, it's a normal distribution. I mean, I think I'll talk about that a little bit later, but
Sure.
it's based off the normal distribution, and
Mm-hmm.
it's usually centered around some mean, and it has and so it peaks up at the mean, and then it's sort of exponentially grows smaller as it at the further and further you get away from the mean. So in statistics, when they usually, you very often assume that distributions are Gaussian, and
Mm-hmm.
it has a very fixed distribution, and usually there is some rough estimates, like when you do statistical tests, if you're, let's say, 2 standard deviations away from the mean, then you say that there's a 95% probability that your outcome falls within two standard deviations, and like 3
Mm-hmm.
standard deviations, like 1/1000th of a, or some much smaller percentage. So
Mm-hmm.
basically, It's the important thing about a Gaussian is that even though you're taking a probability distribution over in an infinite real line,
Mhm.
the 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 probability under the Gaussian, under this bell curve, or under the normal distribution, it's going to be 1. So it gives this nice property that even though you're infinite, you can still, you're working with a finite, you're working with a finite area, even though it's infinitely long.
Perfect. Thank you, Alex.
Okay. Yes, the Gaussian distribution is normalized. Yes, so yes, there's a normal distribution. Well, you can also transform the even. I think you can transform the Gaussian distribution by adjusting the mean and then making it wider through adjusting the standard deviation. Um, it's well. Let me move on.
Sure, go ahead.
Yes, a Gaussian is a bell curve. The bell curve is sort of the drawing of the Gaussian distribution. So next, I'm going to move on to. So let me move on to the basics, and that's going to be set theory.
Mhm.
So we can define a set of objects, and it's common in computer science, and there's some mathematical theory behind it, and it's just a collection. It's a collection of any number of objects, and these objects don't have to be numbers. They could be colors, they could be animals, they could be people, they could be anything that you want them to be. They can be functions. It's a very generalized collection of objects, and you can take subset, and if you have a given set, in this case, in our example here, it would be the set of elements A, B, and C.
Mhm.
You can take subsets of that set, which are smaller sets containing elements which are included in your original set. So in the example here, S1 equals BC. B and C are both contained in the set S.
Mhm.
There's also something called the power set, which is all possible subsets of S.
Mhm.
So for example, if S is exactly A, B, and C, then I went out and wrote out every possible set. So you could have each single element. The empty set, which is the set containing no elements, is a set. Um, the set each singular element, so A, the set containing A, the set containing B, the set containing C, each of those are sets. And then of course, sets, they're the combinations of two possible elements, like A, B, A, C, B, and C. And of course, there's a set containing 3 elements. And one thing to note is the empty set and your entire set S are going to be within the power set of your set. And also you can take unions of sets, and that's if you take 2 sets and then you sort of join them together and you ignore overlaps, or
Mhm.
you don't double count them, I guess, then that will be the union of 2 sets. And there's the intersection of sets, which are what elements they have in common. So if you have a Venn diagram, that's sort of an easy representation of a union. So if you have a Venn diagram of 2 sets, I don't know if I can bring that up real quickly. The stream might be laggy if I try to bring up images. But
Do you have like the capability to draw on your computer? Like maybe pull up Microsoft Paint or something, and if that would be easier for you?
yeah, I'm just worried that if I try to move, oh,
It's okay. Whatever is
okay,
most comfortable for you. Yeah. Oh, there we go.
okay. So
Perfect.
this is a
Yeah.
Venn diagram. So if this is the set A and then this is the set B, then both of those, the overlap of both of those will be the union, and this intersection, which will be this red area, will be it'll be the intersection of them. Okay.
Thank you.
And there's also the complement of a set, and that will be or the complement of a subset, I guess. So if you have, for example, in the example here, if we have the elements A and B, then the complement of that will be every element in the set S, which is not the subset that we're considering. So in this case, it'll be the element C. So it's whatever left over, it's whatever outside of our subset. Okay, and if I'm going, let me talk about this a little bit more. Sets, as I mentioned before, sets can contain anything, numbers, objects. In probability, we're usually going to consider, so probabilities are going to be defined on sets, and usually they're going to be sets of outcomes. And these outcomes could be configurations of atoms. They could be, well, if I roll a six-sided die, one outcome would be 1 is face up, 2 is face up, 3 is face up, and so on. It could be, if you're playing sports, team A wins, and the other outcome could be team B wins. And it could be a more, and the outcome could also be more complex. For example, if I'm doing a lot of different actions, it could be, I could be flipping a coin, rolling a die, and then generating a random, and then generating a number. Let's say between 0 and 1, then it could be, so one specific outcome would be that I land heads and I roll 2 out of 6 and I generate the number 0.15. And maybe the way that I do this might be related somehow. And there's, so when you talk about a system, like rolling a die, there are a lot of different ways you could describe the system. Like you could just describe it as, if you roll a die, it could be which side lands heads up. But you could also talk about, well, you could also include, let's say, the orientation of the die when it, you could include like, well, how it like travels through the air and lands on the table. So it's really up to you how you want to describe this. And one final thing is that probability is not necessarily defined for specific outcomes, but it's going to be defined for sets of sets of outcomes, which are the subsets that I was talking about. And in probability theory, they call those events. So for example, so the probability, it's not always defined on one specific possible outcome, but let's say you're trying to roll a random number between 0 and 1. Technically, the probability is going to be defined on some set of outcomes, and usually that's going to be like an interval. Like, what's the probability, if I generate a random number, what's the probability that it's going to be between 0.15 and 0.2? Because technically, the probability of landing on exactly like 0.16 is going to be 0, because there's infinitely many possibilities, so they can't all have finite probabilities if it's reasonably even. So, okay, any questions? All right.
Yeah, we're good.
Okay, so, and let me introduce two final, I guess, more advanced concepts, which are going to tie into this idea of probability measures. And it's often too much work to spend. So, as I mentioned, we want to measure events or sets of outcomes or subsets. And it's often too much work to specify every single subset that we want to measure. So it's easier to try to generate them instead. And and two ways of doing that is, well, it's the same basic principle, but there's an algebra of sets and there's a sigma algebra of sets. And an algebra of sets is, it's a non-empty collection of subsets. So it has to have at least one element, and it contains the empty set. And it's closed under complements. It's closed under finite unions and intersections. And so let me give some intuition behind this. Usually we're going to start with something like the set of open intervals, and then we'll consider the complement of those, which will be, let's say, the real line except for that open interval. And then we're going to consider all possible sets which are combinations of those through either unions or intersections. And then we're going to consider, I guess, the complements of those as well. And then we're going to keep doing these unions in intersections, and we can do that until we end up with a sort of set of sets, which is well, which is closed, which means any two the union of any two elements, or the union of, or the union of it'll be closed under unions, finite unions, intersections, and complements. And sigma algebra is, and so this will be closed under finite unions and intersections. I'll give an example of that later. And for sigma algebra, it'll be the same as an algebra of sets, but it'll be closed under, they shouldn't say countable, but it'll be closed, well, sorry, it'll be closed under countable unions, which means you can take infinitely many unions together as long as you can enumerate them. And I'll try to give an example of that in the next slide. And we will say, and what we're usually going to do is we're going to start with some subset of elements, and we'll call that like this curly E. And we'll say that the smallest possible sigma algebra containing curly E will be written as this curly M of curly E. And I don't know if that might be a little bit confusing.
Is there a visualization you can share with us?
I have an example.
Perfect, thank you.
2 slides down. And for example, okay, so let's consider the set of natural numbers, which is all positive integers. And we're going to try to generate the algebra from the set of sets containing single even numbers. So we're going to generate it from the set containing 2, the set containing 4, the set containing 6, and so on. So this will include, generating this algebra off of the set of even numbers, will contain all finitely many. This algebra will contain sets containing finitely many even numbers, because we can take the union of all these singular sets containing singular even number elements, and then we can group them all together, and so we can contain sets containing finitely many even numbers, and also this algebra will contain the complement of that as well. So it will contain, for example, the complement of the set containing 2 will be every natural number, will be every positive integer except for 2. So it will contain 1, 3, 4, 5, 6, 7, and so on. And the complement of 4 will be 1, 2, 3, 5, 6, 7, and so on. And the set containing 6 will be 1, 2, 3, 4, 5, and then 7, and so on. And then you can take the union of those, or you can take the intersection of those as well. And if we take the intersection of all those complements, we're going to end up with the natural numbers except for finitely many even elements. So this algebra will have, of course, no matter how we take these unions and complements, it will never have it'll either have 0 odd elements if it's finite, or it'll have every odd element if it's infinite. And that may not be that simple of an example, but this is just, if you just think about a few examples, if you try to work them out on paper, then it might make a bit more sense, and hopefully that sort of helped, maybe not. And for a sigma algebra, let me give an example of that. We're going to talk about the interval containing the open. We're going to generate a sigma algebra from the open intervals. So if we, I don't know if I can draw that. Oh, is it? I don't know if it's, well.
No, you're doing fine, Alex. Go ahead, continue.
Let me know if my voice is, if it's breaking up. So the sigma algebra, this is very common. If we can generate the sigma algebra from the set of open intervals. So if we take the complement of an open interval, it's going to be negative infinity to a, and then b to infinity. And we can take the intersection of those, and we can generate And it turns out the sigma algebra of the open intervals will also contain the closed intervals and the half intervals. And that's what we commonly use for our sort of ideal example. Okay. All right.
Let's get some feedback on the chat room. Is the sound clear, or is it the sound breaking up? I think we're doing
I
okay.
guess. Well, let us know if you have if you continue to have problems.
Yes.
Let me skip this. This was sort of in between, but let me move on to. Okay, sure. So let me move on to some basics of topology. And so we've defined sets, and we've talked about subsets of sets and algebras and sigma algebras. So usually we want to define which subsets are open, because one of the reasons why we can do this is that when we define continuous functions, in order to define continuous functions, you have to define what sets are open, what sets are not open. And let me just mention that when you think about probability, you're usually not going to think about the topology of a set. So don't worry about this too much, but I just want to cover some basics. So the definition of a topology set, the topology of a set, it's a collection of subsets of your set S. So it's a subset of your power set of S, such that the empty set is in this collection of subsets. The entire set is in this collection of subsets, and it's closed under arbitrary unions and finite intersections. And we define a topological space as a set along with its topology. And usually the notation for that is that you'll write this or you'll write this parentheses. It'll usually be something like x comma and then some like curly x or something like that. I am not sure what resources would have good pictures.
Well, here, I found one picture. Do you mind if I share my screen really quickly?
Sure, that'd be fine.
Okay, let's see. So, quick screen share. Okay, and then, so is this visible to everyone? Can you see that, Alex?
Yeah.
Okay, and so how can you describe this for people when it comes to topology, how this would relate?
Okay, so this diagram is showing, so if you have a set, if your set is the elements A, B, and C, where each of these circles is a possible open set. So on the upper left corner, the only open sets are going to be the entire set, and that's called the trivial topology. And the one to the right of that, which there's one circle around A, then the set containing A is an open set, the set containing AB is an open set, and the set containing A, B, and C are open sets. And to the right of that, the set containing B is an open set, the set containing AB is an open set, and the set containing B and C is an open set. And all three of those. And if you look at these examples, if you look at the top right example, you'll notice that if you take the union of any two of these, for example, if you look at the set containing A and B and the set containing B and C, there is a circle, there is an open set which is for the intersection of those, which is just B, and there is a circle which is the union of those, which is A, B, and C. And this is true for any of these pictures. Then you can take the union of any two of these circles, and you can take the intersection of any two of these circles, and they will be present in that diagram. So pictorially, you can see that there are a lot of different possibilities for topologies on a set.
Mhm.
Even the real line, there's a lot of different ways you can define topologies on it, and I was trying to, I think, um, when I
Yeah.
when I was trying to
Do you want
talk
me
about,
to go?
sorry.
Sorry, go ahead. I was
Yep.
just going to say, let me know when you want me to go back to your slides.
I think that should be good. Yeah,
Okay,
let's
great.
go back. Okay.
So I'm going to shrink this down.
Oops. All right. Um, so, so the elements of, so as I mentioned, we're basically defining which sets are open, and the elements of them are called open sets. And of course, what's important is that it'll be relative to that specific topology. If we think about the picture that Laura showed, if we switch topologies, what was open in one topology is not necessarily open in another topology. So it's completely dependent upon how you define the topology. And one other thing, that closed sets are going to be the complements of an open set. And so sort of the intuition behind a topology, and it's sort of what we were talking about when we were looking at that picture, is that some elements, we're trying to get a sense of which elements are close to each other. So if we look at open sets around X, if we look at open sets containing some element X, then they should, to some extent, share some close elements. I mean, so if you keep and that's this idea of finite intersection. So like another example is if you think about the real line, and if you look at open intervals around the real line, then if you intersect them, no matter what, you'll still have this sort of like you can always find this smaller interval, which is within the intersection of overlapping open intervals. Okay. And okay, so what do we have here? An example of that, and I guess we covered it better from the picture, but this is just an example. If you have, if your topology is on the real lines, and you have, if you're defining it based off the open intervals, so the interval from one, so if you're considering the interval from 1 to 3 and the interval from 2 to 4, then the union of the interval from 1 to 3 and 2 to 4 is going to be the interval from 1 to 4. And the intersection of these two intervals is going to be from 2 to 3. And each of those, of course, are also open intervals. So they are also, so this notion of it being, the open intervals being closed, being closed under unions and finite intersections, it works. Another example, okay. Oh, that's useful. So here's another example, and this is actually pretty important, and this is called the discrete topology. For a discrete topology, it's sort of the biggest possible topology. It's where we define every subset is open. So that means every singular element is going to be open, and any combination of elements that you put together, it'll also be open. And the intuition behind this is that you could think of this as so every element is open and closed. And if we try to think of our idea of distance, it means that each element is arbitrarily far apart. It's like, so if we were to place a finite number of discrete elements on the real line, we would say that each of these elements is like arbitrarily far from any other element. So therefore, that no matter, so usually, if you're on the real line, if you take the intersection between, you can find elements which are close to another element. You can find a real number which is close to another real number on the real line. But if you moved all these points on the real line so that they're infinitely far apart, then each of these points would sort of sit in isolation from each other. And that's sort of our, and if you do that, then you're pretty much creating this discrete topology where everything is arbitrarily far apart, so you can sort of create these open intervals around every single point. And the reason I mention this is that in a lot of situations, like if you're rolling a die, or in data science or in deep learning, when you're when you have what are called discrete or categorical distributions, you don't have some nice continuous probably you don't have a nice continuous space. You have a finite number of elements, and usually you're going to be defining your probability on each of these elements in your each of these discrete elements. And hold on, okay. This probably isn't as important, but okay, so as we saw in the picture, the same set can have many different topologies. And when we take a function from one topological space to another topological space, it may be continuous in one topology, but it may not be continuous in another topology, because the definition of a continuous function is that the sort of the pre-image of an open set is going to be open. Okay. Right. Okay. And intuitively, we can shrink or expand, and this is why topology is sort of important. When you see pictures, sometimes when you hear about topology, you see pictures of like smushing spheres into bricks or into pancakes, or stretching out objects, and it's that we can shrink or expand sets from smaller ones into larger ones using functions, and one of those functions will be our expected value function onto the real line, and that can project or transform these topologies. So here I try to make sort of a figure which is it's like the one above, but in this case we have more elements, but we're grouping all these elements together. So A1 and A2 and A3, that'll be an open set. B1, B2, B3, that'll be an open set. C1, C2, and C3, that'll be an open set. And we won't be able to divide it any further. And we can form a mapping between this topology to the one above. We can say that sort of this group, these three elements, A1 and A2 and A3, can map to A, B1, B2, and B3 can map to B, and so on. And we can say that even though this has more elements, this has an equivalent topology as this smaller one above. All right, and let me move on. So I mentioned algebras and sigma algebras when we're talking about this, set theory. And once, of course, a topology is a collection of sets, so we can use it to generate a sigma algebra. And when we do this, this is called the Borel sigma algebra, and we denote this by curly B of X, where X is the topological space. So basically, we're going to start with our set of open sets, our topology, and then we're going to do all these complements and unions and countable unions and countable intersections, and then we're going to keep going. And once we do this process, we'll end up with some larger set of open sets, or some larger set of sets, and that's called the Borel sigma algebra. And this is what we're going to this is what we will be considering to be measurable functions. And as a small example, when we talked about the sigma algebra of open intervals, as I mentioned before, it turns out to include closed intervals and half intervals as well. And sort of as a final note, we can create a product space for, if we have two different topologies, we can sort of take the Cartesian product of those two topologies, sort of like, so it would be a two-coordinate space, and the first coordinate will be based off the first topology, and the second coordinate will be based off the second topology. And we can also create sigma algebras in this product space as well. And this is important to the formulation of vector spaces.
Hey, Alex, I found an image for the Borel sigma algebra. Do you mind if I share that?
Sure.
Okay, let's see. This might help people get a little bit more of a visualization and tell me if this is helpful at all. Let's see. So how can you describe this image in relation to Borel?
I'm not sure. That
Then maybe that was a bad example. Okay, so let's find a better example here. So
I can't think of any. Well, it might be hard to picture. Well.
yeah, I was hoping to find a visualization, but that's okay. We can move on, and then maybe I'll find something else later and post it to the group as well at that time.
Okay.
So let's continue with your slides.
All right. And finally, we're going to move on to measures and measure theory. And so for calculus, when we integrate, we're inherently using this Lebesgue measure, and that's defined. And for a Lebesgue measure, it's the only measure. Well, I believe it's the only measure that over an open interval, let's say from A to B, the Lebesgue measure of that interval is going to be B minus A. And if it's a closed interval, it's still going to be B minus A. If it's the half open interval, it'll still be B minus A. And if we think back to calculus, when we're performing integrations, if you're doing Riemann sums, then you're taking the height and then you're multiplying it by sort of the width. You're multiplying it by the width of your little rectangle, and you're using that to approximate the area under a curve. And so there's this assumption that we can figure out what this distance is between 1.5 and 2 and 1 and 1.5 and so on. And this distance between these two numbers, this is determined by the Lebesgue measure, and of course it's simply going to be the absolute value of the distance between these numbers. However, you don't, if you think about it, you don't have to do this. It doesn't have to be strictly this absolute value. You could transform it. For example, it could be twice as large, or the further away you get from zero, you could artificially increase this distance more and more. Let's say, and you could scale it by some function f. So, sorry. So this integration is complete. When we perform integration, we inherently assume we're using the Lebesgue measure, but you can perform integration on other measures as well, as long as you can specify what those measures are. And in fact, we can use a function to alter our idea of distance when we're talking about the measure of, let's say, of a subset, such as an open interval. And this is actually a really important concept in functional analysis, and it will be briefly coming up later. We can use a function to alter a measure to create a new measure. And similarly, we can transform a probability distribution into a new probability distribution by applying a non-negative function, and it will be creating a new measure. And so you can actually, so when you think about this integration, you can also think of this function as a transformation of just our flat Lebesgue measure into a new distribution. So our integral, you can see it as the creation of a new measure for your space, and it's this really interesting concept. And actually, there's something called a radon-Nikodym derivative, which is, you can say if you look at it the other way around, if you have one probability distribution or one measure, and then you have a second probability distribution, if you want to change from one probability distribution to another probability distribution, then the way there there's something called the Lebesgue-Radon-Nikodym theorem, which says that there is a function which allows you to transform between one measure and another measure, and it's given by and that function, this change in measures is f, I guess in this case. It's called the radon-Nikodym derivative, and I won't. It's something that you might want to read more about and think about. It's not going to be. It'll be. Sometimes you'll see it in some research papers, but it's very interesting. Instead of just thinking about simple concepts like integration, you can think more abstractly about it. And when we asked earlier, what is a Gaussian distribution? I'll show the formula. I can show the formula later for it. I have an example. But the Gaussian distribution, it's usually represented by this integral. And this integral, but that probability distribution, that integral that we use to represent the Gaussian distribution is actually this radon-Nikodym derivative for the change between a Lebesgue measure to the Gaussian distribution.
That sounds really fancy, Alex. It's awesome. I'm gonna look that up right now.
It's one of those things where you can sort of change your interpretation of how you think about mathematics and probabilities and probability measures. So let's formally define what a measure is. A measure is defined on a set X and a sigma algebra of X. So a sigma algebra, it's defined on an X and a sigma algebra. So remember, sigma algebra, it's closed under these complements and countable unions. This measure mu, so this mu is going to be a function on the subsets of X, and it has to be non-negative because intuitively, when we think about it, if we want to take the measure of, let's say, an interval, it shouldn't be less than 0. It should be greater than, or if it contains just a point or if it contains nothing, we want the measure to be 0, and otherwise we want it to be greater than 0. And there are exceptions. There are sort of fancy mathematics where you have negative and you have complex measures. The measure of empty set should be 0, although other subsets can have measure 0. And I guess I didn't have a nice picture for this. And there's something called sigma additivity. So for this, if you have a whole bunch of disjoint sets, you want the measure of the union of all these disjoint sets to be the sum of the individual measures. I don't know if I can get a picture of that. And one of the problems with preparing these slides is that it's hard to, it's laborious to create all these pictures in PowerPoint.
It is, but everyone really appreciates your efforts. So thank you so much for taking the time to do this.
Yeah. Well, I don't have a great picture. Well, maybe if I could get like a real line picture, real line. Sorry about this. Hopefully you can see my mouse. So if I show, all right, here we go. So here's a picture of the real line. And so for sigma additivity, what we want to do, let's say we're taking, we want to evaluate the measure of from -3 to -2 and -1 to 0. So for sigma additivity, we want our measure to have the property that it's literally going to be the sum of this measure from 3 to 2 and the sum of the measure from -1 to 0. So it'll be strictly additive, as long as they don't intercept. Of course, if if we have an interval from -3 to -1 and -2 to 0, of course they overlap, so it doesn't count because you don't want to count -2 to -1 twice. But inherently, this is sort of this idea of distance that we want. Oops. And another thing that I want to mention is that, so actually probability spaces are just measure spaces. They're defined with they're defined on a set. You have a topology, and you have a probability function, which is a measure which adds up to 1. And one thing I want to note was that many probability paradoxes exist because you're actually defining different probability measures maybe on the same set of outcomes. So if you were to spend the time to carefully think about, well, what is my so yes, I have a probability of a system, but how am I defining it? You'll see that you might be changing the definitions of your probability function or your measure function in a way, and that's actually why you're ending up with these seemingly paradoxical results. The darker side of PDFs.
Yeah, I'm not sure what he means by darker side. We did have one question a little further up. Let's see, where is that?
Sample sizes of
Okay.
interest.
Yep. So topologies are kind of like sample sizes of interest. Would you describe them that way, Alex?
I don't think so, although I don't quite understand what sample sizes of interest means if he were to elaborate on that.
Sure. And there is a little bit of lag between the video and the text, so we'll give him time to respond. But go ahead with your slideshow.
Right. Okay. So let me continue along to some of these very many mathematical concepts which are laying this foundation, and that's called metric spaces. So this is going to be another idea of distance. So our intuitive ideas of open sets is open intervals. And of course, on higher dimensions, instead of open intervals, you tend to use open balls. So there'll be n-dimensional spheres which have a certain radius, let's say P or R, and you can use these open n balls to form a topology on let's say the Rn, which is the n-dimensional space of real numbers. And since the open balls create a topology, since you can define open sets through these open balls, you can form a Borel sigma algebra on it, which means that the open n balls you can generate a measure space from these open n balls. So all we need to do is in order to do that, we just have to find a way we just need a distance function between one point and another function, and this is called a metric. And the properties of this metric will be that p of so let's say our distance function is p, and it's going to be from 0 to infinity. And we want the distance from x to y should only be 0 if x equals y. And that sort of makes sense. If x is a little bit further away from y, then there should be some distance involved. Okay. It should be symmetric. So if the distance from x to y should be the same as the distance from y to x. And finally, and this is something, it should satisfy the triangle inequality. So the distance from x to z. So if you're trying to move from x to z and you take some intermediate path, well, let's say to y instead. So the distance between x to z should be less than or equal to the distance between x to y and then the distance between y to z. So you can think of that. Well, I'm sure there's some picture of.
Yeah, I included one image. We can see if it's helpful. Here, I'll share really quickly. So let me know if this one is helpful with your description. What do you think?
Is it might be lagging. I'm not. Oh, is this for metric spaces? Okay.
Yes.
It might help a little. Well, let's see. We have. So here, it's reasonably useful. So for here, this is showing the distance between y and x0. Where is x0? Oh,
Mhm.
and I mean, it's basically so in our nice real number space, it's just going to be the line in between there. So I'm not quite sure. Well, it's sort of an illustration. So, okay, I think I see what they're trying to do here. So here they're looking at, they're focusing on this point x0, and then they're going to draw a ball of radius r around it. And then here we're considering this point y, and y is less than r. So notably that y is going to be, because y is less than r, it's going to be within this ball of radius. It's going to be within this ball of radius r. And I guess here if we draw a smaller ball around y, we'll see that it's also contained inside this.
Great.
Yeah.
So I'll go ahead and go back to your slides now.
Will the topology of tangent of arctan layers be covered during the presentation? I don't think so. It's at some point we do have to get around to the probability part of probability. And I know that I might be taxing people's interests
That's
enough
okay.
as it is.
We'll continue as long as cover as much information as you would like to cover. And then, of course, they do have your slides as an additional resource.
Yeah.
And, we can look up videos, tutorials for people and post those as well. So if there's anything else that you want covered, also, if you want to share resources, that's the goal here. We're just trying to help each other learn. So yeah, let's just continue.
Okay. And let me just give a few comments on metric spaces. As I mentioned, we can form, remember our intuition is that we want to form these balls of radius r around a point x, and we can actually define sets which are balls of radius r now that we have our metric. And as I mentioned, these can be the base of a topology. And because of a topology, once you have a topology, you can define a Borel sigma algebra off of that topology. And so also some examples of metric spaces. First of all, there's Rn with the our n-dimensional, in Rn, you can use our normal Euclidean metrics, and that's defined as, well, like, it's the Pythagorean theorem, the square root of the differences, the square differences of each of the coordinates. And this is called the L2 distance, and actually, they often use this L2 distance when they do regularization, because they tend to, it's a common idea, it's a common concept of distance, and sometimes they add this to the loss function in order to encourage the loss function to be, to encourage the parameters to not have overly large values. Okay, I'm glad that people are enjoying this. Okay,
Yeah.
and another example is something called the total variation distance. And this is going to be a bit more abstract, but remember when I said sets could be anything? Well, in this case, we're going to consider the set of probability distributions. And you can try to, and we're going to try, and for the total variation, you're trying to find the distance between two probability distributions. And the way it's defined is that you're going to be taking the difference of these probability distributions, PR minus PG, and you're going to you're going to evaluate this for every possible, and this PR minus PG. It's going to be some sort. It's going to be like an integration. It'll be like integral PR minus integral of PG over your space, and you're going to be doing it for some subset of your entire space. You're going to be doing it for a subset of your of the entire probability of the entire probability space. In this case, A, and maybe. So, for example, if there's a probability function on the real line, you could evaluate the difference between these probabilities on just the negative half of the real line, or it could be on the positive half of the real line, or it could be from, you could just be evaluating from 0 to 1, or it could be from 0 to 10. So you can define this difference in probabilities for every possible measurable set A, and the supremum of that. So if we take the upper limit of all those possibilities, that number is going to be called the total variation distance of two probability distributions. So KL divergence, it's similar. It's yes, so KL divergence, it's something similar. You're going to be trying to find the distance between two probability distributions. The only difference is that the KL distribution technically is not, so here we talked about symmetry and the triangle inequality, and the KL divergence turns out not to be symmetric. So the KL divergence between PR is not equal to the KL divergence between PG and PR. So because of that, it's sort of a weaker form of a metric, and they call it a divergence. And we're actually going to be talking about the KL divergence in more detail, as well as other types of distance metrics or distances between distributions. And that's a good question. So as I mentioned before, metric spaces provide a general idea of distances, using distance, but not so for information theory. So Euclidean distances, that would be the L2 distance, that would be the Pythagorean theorem sort of distance that we talked about before. But when we work with information theory, we're actually not going to be using Euclidean distance. We're going to be using something more based off entropy, and KL divergence fits more nicely into that. So in math, once we have metric spaces, we have this idea of distances, and if we once we combine that with the notion of vector spaces, we can now do calculations on lower dimensional manifolds, or where I guess I shouldn't take the time to define manifolds, but so for example, if you have a two-dimensional object like a sphere in a three-dimensional space, then that's considered a submanifold of the three-dimensional space. But because this sphere is two-dimensional, we would actually like to be able to use our two-dimensional calculus to travel along it, to determine distance, to perform calculations. Metric spaces along with vector space, vector spaces allow us to do that. And actually, this is why we want to generalize this idea of a metric. If you work on, let's say, two-dimensional objects in three-dimensional spaces, you can't use, remember this space is curved, so you can no longer use this idea of Euclidean distance anymore. You have to alter your metric to, and that's going to depend on how the manifold is curved. So the metric is not always going to be the simple Pythagorean theorem idea of distance. So your metric will change, and well, that's sort of the area of differential geometry and differential manifolds. And also, and also metric spaces can apply to natural images or this idea of lower dimensional manifolds can apply to natural images or natural words. For example, if you're thinking about word spaces, words, you could think of each character having I guess, a possible dimension. But the natural words aren't going to be any arbitrary sequence of characters. For the English language, you can't just string a whole bunch of consonants together and consider that a word. So it's actually a much, so the space or the manifold of natural words is going to be much smaller than all possible combinations of letters. And the space of natural images, when we do image processing, it's actually much smaller than just arbitrary pixel values in a grid. So in deep learning, we're actually deep learning. It's not trying to work on these. It's not trying to optimize itself on all possible images. It's going to be it's optimized around natural images, sort of like the ones that we see and that we can represent. If we as humans saw this image of just complete noise, it would mean absolutely nothing to us. So when we do something like image classifications, we want to optimize it around images that are meaningful to people. Okay. Let's see, what's the last comment? Later on, we'll be working in parameter spaces to define the parameters of a model. Oh yeah, this is actually a pretty interesting, but a bit more advanced. When we're working on parameters, so parameter space, so later on, when we have deep learning models, they'll be defined by the parameters. Which will be weight matrices and maybe biases as well. And you can think of these parameters to be a parameter space. Like if you have 100 different parameters, then the parameter space is this 100-dimensional space. But remember, and we'll cover this later in chapter 6, we use gradient descent in order to optimize these models. But one of the inherent assumptions of gradient descent is that you're working off a Euclidean metric. So you're working off this idea that distance is based off the Pythagorean theorem. But you don't necessarily know that these parameter spaces follow a Euclidean metric. And it turns out that when the metric changes, if you have a different metric, your gradient descent may no longer be efficient anymore. So there are actually some tricks which can adjust the gradient so it'll to fit the metric of to fit a more realistic metric of these parameter spaces, and that can actually have more efficient gradient descent. And actually, batch normalization and layer normalization are based off of, well, they're theoretically, they fulfill that function. And it's a very advanced, interesting idea, and it's actually fairly recent. So this part I want to gloss over because it doesn't, it's important. I mean, it's more generally important, but it doesn't fit that as well into probability theory as much. But it's this idea of vector spaces and norms. So a vector space, so for a vector space, you want to be able to add two elements together, and you want to be able to do scalar multiplication. So this is not necessarily true in an arbitrary topological space. For example, if you just have a set of letters like A, B, and C, like it's not clear what A plus B equals, right? It doesn't make as much sense. But if you're working in the real line, if you have some Cartesian coordinate system, then it makes much more sense what the ordered pair 2, 3 plus 4, 5 equals, because you can do. And also, if you're working in a vector space, if you take an element like 2 and 3, you can multiply it by a scalar value. So you can multiply 2, 3 by 3, and you'll end up with 6, 9. And that's usually what we see more in the real world and in sciences. And it's more common. Well, it's much more common. I just wanted to mention this because technically one of the when we perform differentiation, sort of the other end of calculus from integration, then you usually assume that you have vector spaces. And for this I tried to, so these earlier concepts I tried to be more intuitive about it or somewhat intuitive about it, because I wanted people to sort of understand what was going on, but I didn't want to go too far into vector spaces and norms, so I'm just going to give the definitions real quickly. A norm on a vector space it's sort of like another idea of distance, but it's the distance from 0. And it has these rules that the absolute value of x is the norm of x is 0 if and only if x equals 0. You have the scalar multiplication rule, and you have this triangle inequality rule as well. And so, and notably, the one thing I wanted to mention was a norm. So a metric is based off of two different values. A norm is based off of one value, but a norm can be used. Once you have a norm, you can define a metric because you can, in a vector space, you can add and subtract two elements. So if you have a norm, you can define a distance function by just subtracting two elements and taking the norm of it. And once you have a norm, you can do differentiation. Well, we shouldn't worry about this too much, but this is basically defining derivatives. Okay, so finally we are defining probability spaces. And so that was a much longer explanation than chapter 3. Or this is just leading into probability spaces, but it was a much longer explanation than Goodfellows, which is, I thought, might be important because I think in the chapter he writes that random variables are variables that can be defined randomly or something like that. And yeah, sort of, but you're missing a lot, and hopefully this is going to fill in some of the gaps. So a probability space, remember we talked about measure spaces, and a probability space, it's just going to be a measure space where the total probability is going to be equal to 1, because intuitively, you can't have a probability of greater than 1. So if you consider the probability of all possible outcomes, it should add up to 1. And of course, the probability should be greater than or equal to 0. And the probability space, so let's talk about the formal definition. It's defined on a set, which in probability theory, they usually denote as big omega. It's going to be, there'll be a Borel sigma algebra, which is denoted by large sigma, and a probability function. And this probability function has Kolmogorov axioms. And so the probability of any set, it has to be greater than or equal to 0. The probability of everything has to equal to 1. And this is finally the finite additivity condition, or the countable additivity condition. And that is, if you have a bunch of disjoint sets, if you have if you have a countable number of disjoint sets and then you add them together, you can add up the individual probabilities of each of these components or each of these smaller sets, and it will add up to the total probability. Oh, is it choppy?
It was for a moment, but it's cleared. So remember, they're lagging a few minutes behind us. It's okay.
Okay. And there's also a formulation with finite additivity instead of countable additivity. So in that case, then instead of saying you can do this additivity for a countable number of sets, you have to make sure that you can only do it finitely many times. And in that case, you have much more restrictions. Instead of sigma algebras, you're working with algebras. So let's see. And well, so if you're comfortable with the idea of measures, as I mentioned, you'll notice that probability spaces are really just measures, only with the probability equal to 1. So hopefully by talking about measure theory, we finally got some intuition of what it was. So let me give some examples of probability distributions for categorical and discrete distributions. Usually we use the multinomial distribution. So if you've heard of the binomial distribution, it's so if the probability of flipping a coin is going to be, let's say, p, then the probability then the binomial distribution will just be the binomial distribution for landing one head out of n. It'll be like n combination. It'll be n combination 1, and then p to the 1 times 1 minus p to the n minus 1. And this is just a generalized form because I was running out of time and I didn't want to, it actually took a lot of time to write everything in LaTeX and then to write a lot of expressions in LaTeX and import them over into the slides.
Oh, wow. So just for a side note on that, when I did the presentation last time, I found images that were already done online, or I did screenshots directly from the textbook and then included those in my slides. So we really appreciate your efforts here, Alex. That's amazing that you took the time to do that.
Yeah, it was, sometimes I wasn't able, sometimes I just wrote it out in like shorthand, and you'll see that a bit later in some of the later explanations. But yeah, it looks a bit nicer. But yeah, it makes you appreciate, I guess, the professors who actually put together full presentations. This is
Yes.
actually a lot easier on a whiteboard because you can just sort of write out all these things by hand, and you don't have to prepare everything beforehand. But anyway,
Right.
so for continuous distributions, then I'm going to mention, I wanted to mention the ones they covered in the book. So we asked about the Gaussian distribution earlier. And here is this is the probability distribution function formula for the Gaussian distribution. And it's like this 1 over square root of 2 pi sigma squared is this normalization to make sure that the total, when you integrate the probability over the entire space, that it's going to be equal to 1. And then it's this exponential function. It's like x minus the mean divided by 2 sigma squared. Copy paste. Well, the problem is like the problem, it wasn't about copy. It was that Google Documents' slides doesn't accept, like, it's I don't know. It didn't. It was pretty bad about accepting formulas. So you can copy pictures over directly,
Yes.
but it was very inflexible.
Yeah, to just type them in. Yeah, that would be difficult.
It looked really ugly. And anyway, so he also mentions the exponential distribution, which it's a distribution which exponentially decays for positive values. For negative values, the probability is going to be 0. That's what this 1 x greater than equal to 0 is. This is called a characteristics function. It means that whenever x is greater than or equal to 0, whenever this condition is fulfilled, it's going to be 1. And whenever this condition is not fulfilled, it's going to be 0. And they're just using this sort of as you could think of it as like a gate. It's just controlling which values. It's like a way of controlling which values you want to consider. Otherwise, you'd have to say, like, if x is greater than or equal to 0, then it's lambda exponential function negative lambda x, and for x less than or equal to 0, it's going to be 0. And you'll notice this lambda here is this normalization constant as well, to make sure that when you integrate over it, that it's going to equal 1. And I think Goodfellow mentioned this because it peaks around. So this is exponential decay, so it rapidly becomes smaller and smaller, and this peaks around 0. And there was actually a paper, I think, what paper was it? I think the Gumbel, they're using something called the Gumbel. They're using Gumbel distributions in order to generate categorical distributions, and it was called like the Gumbel Max Softmax. It's a recent paper from, I think, either December or January, and they're using something similar to this. Sort of, they're using something similar to this because the exponential distributions tend to have some special properties when you like sort of add them together. Okay, and he also mentions the Laplace distribution, and this is a distribution which is going to be peaked at around x equals mu, and the width of it's going to be controlled by this gamma parameter. And this is sort of a clever distribution which allows you to, which is has a property that you want, namely that the distribution peaks sharply at a value that you want, and it sort of falls off around them. And in statistics, which is unlike deep learning, they tend to assume that, okay, we're going to assume that our data or our system follows this sort of distribution because we can actually solve for these problems. And if it didn't fall, if your distribution was not a well-defined distribution, then sometimes you can't really perform meaningful calculations. But deep learning, it's different because often, especially for data distributions, you tend not to make assumptions on them. You tend to just say, you tend to just use sampling in order to define the distribution and in order to perform calculations upon it as well.
Yep, so we have a quick question here. Can you please give some examples where Laplace distribution is used?
I can't think of, I'm not sure myself, but I guess you could look it up. Maybe somebody else could answer that.
Yeah, definitely.
Yeah, it's, oh, I guess I didn't have it here. So I think Goodfellow also mentioned something called a Dirac distribution. So a Dirac delta function is basically, it's a limit of a probability distribution that it sort of peaks. It's sort of a point mass which has probability 1 around a certain point and 0 everywhere else. And if you read the chapter, he talks about, well, technically, it's not, you can't represent it as a probability distribution. So what you do is you create a, you say that it's a limit of a bunch of other distributions. So you create something which has a high mass at a single point, and then you take another probability distribution which is even more steeply peaked at that point, and then you keep doing that, and the limit of all those will approach the Dirac delta distribution. But in practice, what's most important is it's a distribution which has all of its probability mass centered around one specific point. Huh?
Great, continue.
Okay.
Yep.
Sorry.
That's okay.
I was just going to comment. So mixed distributions. So yeah, I was just trying to give some examples of probability distributions. So mixed distributions, of course, if you have many different distributions, you could think, well, why can't I just average them together? Why can't I average multiple ones together? And you can certainly do that. And you can average a bunch of distributions together to form a new distribution. I mean, and a common one's called the Gaussian mixture distributions, where you take a bunch of normal distributions or Gaussian distributions around various means and variances. So they'll have different peaks at different areas, and then you can average them together, and then to form a mixture distribution which will have several peaks in several different areas. And also, if we look above for these definitions of normal distributions, exponentials, and Laplace, we can see that we can create a lot of different Gaussian distributions by changing the mean sigma and changing the standard deviation. Sorry, the mean mu and the standard deviation sigma. So you can change this as you vary these parameters. You can come up with a lot of different distributions. For the exponential distribution, you can change lambda, and for Laplacian, you can change gamma, usually to control the width. And actually, you could think of these parameters as latent variables, and you can use these parameters to define mixture distributions. For example, if you were to create a Gaussian mixture distribution, you could take a bunch of different order pairs of mu and sigma, and then create Gaussians from each of those and then add them all together. And these latent variables would now be defining the parameters for your Gaussians and hence for your mixture distribution. And finally, like what I mentioned before, deep learning works with data distributions. Usually for deep learning, we are actually we often don't have to define data distributions as much as in statistics because there is a data distribution, but it's often too complicated for us to understand or to try to predict. So we're just going to, instead of doing that, we're going to approximate it through sampling. And this slide, I'm not sure if it fits here exactly, but it was just sort of an overview of, like, we talked about all these different concepts. We talked about algebras, we talked about sigma algebras and Borel sigma algebras and so forth. And I was going to draw this sort of nesting picture of all these. But basically, you can generalize more and more, and you can form and you can get stricter and stricter conditions. And I just want to give a sense of how these are all fall into place. Like, an algebra is weaker than a sigma algebra because algebra is countable, or algebra is finite unions, and sigma algebras are countable unions. Once you have a sigma algebra, sorry, a Borel sigma algebra, you define a topology and then you use it to generate your Borel sigma. You use it to generate your sigma algebra. Measurable spaces are defined on Borel sigma algebras, and you can define, and we can form an even stricter interpretation. If we have a distance metric, then that naturally forms a topology using n balls, as I mentioned before. And finally, if you have normed vector spaces, then a norm defines a distance function. And a distance function defines a metric. Sorry, a norm defines a metric, and a metric defines a topology, and a topology defines a Borel sigma algebra, and so on and so on. So, and in most cases, and that's why I mentioned at the very beginning that this ideal situation where we have Rn, where we're using the open intervals for topologies, because that's what will in practice we'll use those most commonly, and we often don't have to worry about all the other stuff. But it's good to know because sometimes there are exceptions. Sometimes you have much different spaces, like you might have a space, your space might be it might be continuous in some points, and it might be discrete at other points. Okay. Cauchy, Laplace and Cauchy distributions. Okay. All right. Algebra is only closed. Okay, that doesn't matter as much. So let me move on to random variables, which is like page 5 or something in the actual chapter. So we're moving very, very quickly here. But we're actually going to move a lot faster. So a random variable is a mapping from a probability space to the real numbers. So let's say a random variable. So you begin with a probability space, and it might be something that's not numbers. So it could be like you roll a die, and each of the whatever lands heads up, that's going to be one of the possible outcomes. And that's not really a real number space. But if you can create a random variable. You can apply a random variable function to it by saying, well, the number that lands heads up is going to be our random variable function. So if one landed face up, then we're going to say f of that outcome is going to be 1, and if 2 lands face up, it's going to be 2, and so forth. So this is actually the definition of a random variable, and in science, it's closer to this idea of observation, because yes, there might be a complicated system, but when we are talking about measurements, we're talking about, like, if we're measuring the height of something, or we're measuring the weight of something, or some value, then it's usually a measurement of that system as opposed to some complete description of the system itself. So you're actually moving from this complicated probability space with a lot of different outcomes, and you're sort of compressing all that information into some numerical observation, and that's actually what a random variable is. And one thing to note is, well, so if we have any function, will it necessarily work to create a random variable? And not necessarily. Okay, so it has to be a continuous mapping because what we want to do is we have a probability space and we want to map it to the real line. So we want to induce a probability distribution on the real line as well. And this only works if the function is continuous. And I mentioned before the topological definition is the preimage of every open set is open. And I think I prepared some of this information for a more mathematical presentation. So I got into some of the details, but so maybe I'll skip over that a bit more. But basically, we want to make sure that we're projecting like. So when if we have a random variable function, we can define, we can try to define probabilities on the real numbers by looking, how would I say this? So if we take a topology on the real numbers, I might have this in the next slide. Okay, maybe not. Okay. If we take a topology on the real numbers, let's say we're defining the measurable sets to be the Borel signal algebra based off the open intervals. We can try to define the probability on any open interval by looking back to our original probability space, by looking at, I think a picture might help, but I don't have one at hand.
What kind of picture are you looking for? I can see if I can find one.
I guess, I'm not sure, I'm mapping. Maybe I have paint or something.
Yeah.
Draw very ugly pictures.
That's okay.
So, if, here we have our probability space, and here we have our real line here, and okay, I don't use paint enough to do this. I don't know. Well, so let's say this is the real line, and so we have a function f, and I don't know how to make text boxes. Anyway, so we have a function f which maps from.
If you press the A up next to the paint bucket, so you see the paint bucket.
Oh, okay.
Yep. Press the A, and then you can.
All right. Oh, that doesn't look very good. But anyway, so we have this function f, which is mapping this probability space to the real line.
Mm-hmm.
And then here I'm trying to pretend I have some open interval.
Mm-hmm.
So a bunch of elements, and let me create, I don't know, dots. Yeah, this is advanced stuff here.
You could also just use the pencil. If you click on the pencil, then you can draw freely.
All right. So for this function, let's say, okay, so we have an open interval on the real line, and we're going to think, so we have a function mapping the probability space to the real line. We want to consider every element which maps to this open interval. So every element in the probability space which when you apply f will land inside this open interval. Okay, and this is called the preimage of this open interval relative to f. And so this is what I'm trying to say here, that this so if this set is measurable in our probability space, since our probability function p is defined on all measurable subsets, we can evaluate the probability of these set of outcomes, and that's the probability of these set of outcomes we can naturally map to. We can say the probability of this interval is the same as the probability of these set of outcomes on this space. Oops. So, and of course, this only works if our function is continuous, because we don't always know that for any arbitrary function, this preimage may not be measurable, even if this open interval is measurable. But if f is continuous, then by definition, then this is measured. If this is open, then if this open interval, if this is open in R, and f is continuous from here to here, then by definition of continuous, then this will be open in our probabilities in our topological space here, which means a probability function is defined and it's measurable, and we're happy. Let's see, where was I? Okay. And it turns out that this extends to, there's something called a function is measurable, and it's a stronger condition than continuous. I believe it's stronger. No, it might be weaker than continuous. But basically, it means that if we're considering a subset of the real numbers which is measurable, then this preimage is measurable as well. So the probability is defined on the real line, or the probability of our random variable is defined from our functions and our topology as well. And that's, so I talked about here for measurable mapping, and I didn't want to go into this in too much, but let's see, yeah, I went through a few situations, like if they're topological spaces, then every continuous function is measurable. If they're metric spaces, every continuous function is measurable. Open sets are in the, and this is just a proof of, this is just a short explanation, mathematical explanation of those. Anyway, let me move on before we get too stuck. So for random variables, for the discrete case, every subset of sigma is open. So it's in the Borel set. This explanation might be too technical, but basically for a discrete topology, every point is considered an open set. And remember, open sets are considered to be measurable. So since every point is measurable, that means there's a probability distribution defined on every single point in the discrete case. So for example, again, if we have a six-sided die, each, like one being face up and two being face up and so forth, each of those are considered to be measurable outcomes, or are considered to be measurable outcomes. And so in order to, so in the discrete case, to define sorry, if we have a random variable, all we have to do is we have to add up the probabilities of each individual case. And it's, I guess, I don't know if that sounds more complicated than it is, but basically, if you have a bunch of finite possibilities, to figure out the probability for some subset of those, just add up the probabilities of each of the individual components.
That makes sense to me.
Okay.
Yeah.
And if we think back to when we talked about earlier about the classical probability definition, where each outcome is equally likely, then that's very similar to what they're doing there. Actually, it is what they're doing there, only with the probability being equal at each point. So for the continuous case, and this is something that everybody learns when they learn probability, but when you think about it, it doesn't make as much sense. So for the continuous case, remember that the probability, if you're looking on the real line, the probability of any single point is usually going to be 0, because there's infinitely many points, or there's infinitely many points, and so they can't all have values greater than 1. But we also have this idea of probability density. So the question is, well, what is a probability density? Like, what is a probability density? Because that seems very different from our discrete case. In our discrete case, we just added up all the probabilities of individual events. But in the continuous case, we can't just add up the probability of each point in an open interval, because the probability of each point in an open interval is 0. So it doesn't work nearly as well. So in order to explain this, we start with cumulative distribution functions. So the cumulative distribution function is a probability. So if we have a random variable, if we have a random variable x, the cumulative distribution function is a probability that x is less than or equal to x. And notably, remember our random variable is mapping to the real line, and the interval negative infinity to x is considered to be Borel measurable because it's an interval, which means, and because it's measurable, and assuming our random variable is continuous, that means that there is, if we remember this badly drawn picture from probability spaces to the real line, if this is measurable, that means that the probability is defined, because the preimage, the points leading to this measurable set, the points which map to this measurable set has to be measurable as well. Yes, so the points that map to that set have to be measurable as well. So therefore, the probability must be defined. So for a cumulative distribution function, because we're mapping to an interval, anytime we map to an interval, we know there has to be a probability. There has to be a probability measure that we can evaluate on the preimage, which I sort of represent here. So the probability of x being less than or equal to x is the probability on this probability space of the preimage. I don't know if that's that clear.
No, that's great. Continue.
Okay. So the cumulative distribution function is actually has some meaning in terms of our probability theory. So the question is, well, then what is our probability distribution function? That's usually our point probabilities. And that's a bit more confusing, because remember, the probability at any specific point has value 0. So our probability density function is obviously not the probability at that specific point. Okay, so what it is, and let me draw something here.
You can also erase if anything that you don't want there with the eraser. Yeah.
Yeah. Resize. No. Whatever. Okay. Yeah, this is terrible. Okay. Size. Anyway, it's not that important. Anyway, so let's say we have a probability distribution function. So we can explain what a probability density is. Remember that our probability, because we have a cumulative distribution, probability is defined on open intervals, right? So for a probability distribution function, what we can do is, if we're at this point x, we could try to increase our interval by a very small amount. You could call it h, or you could call it delta, or whatever. And so this increase in probability, so by increasing this interval by a small amount, we are increasing the probability of this larger. We're increasing this probability from whatever the probability is from here to the probability of this larger interval. And you can think of this difference in the difference in the probabilities of these two intervals as sort of like the probability density. And in fact, so you can start with these larger intervals, but then you can gradually make smaller and smaller intervals until they approach your original interval. So you could try to make it as fine as possible. And in mathematics, that that would be taking the limit of it. So the probability density function is basically this marginal increase in the cumulative distribution function as it's this marginal increase in the cumulative distribution function at a specific point. So for, let's say, a Gaussian distribution, it would be, well, if you have a bell curve, something like that, and you're at this point here, the probability density function is basically, well, I'm increasing this I'm increasing my probability by this small amount, and if we think back to what integration is, this distance is the height of this distance is going to be the probability distribution function x, something like that. It's sort of a terrible drawing.
That's okay. We got it's p times x. I just want to be a little bit aware of time. I know we're going on about 2 hours now. So that's okay. No, I mean, it's great. You're giving so much in-depth information here. But I would say if we could make sure just to hit the most relevant slides that were covered in the book. And then, of course, your slide share is a great resource for people to refer back to as well. So maybe pick your last, like, 4 or 5 favorite slides, maybe ones that have some pictures on them, and that'll give people more imagery that they can associate this with. Yeah.
Yeah, let me try to skim through the rest.
And of course, Alex, I'm going to ask you if you're comfortable with people that have questions afterwards, maybe if you would be willing to share your contact information, if they could ask you questions, would you be comfortable with that?
Oh, absolutely. And we can post it in the chat. You can have my email.
Perfect.
So where was I? Expected value. So yeah. So expected value. Remember, at the very beginning of I had a slide about, well, how do we evaluate our loss functions? And our loss functions are evaluated through expected values. And expected value is basically, you have a function on your random variable. So you have a random variable x, and you're applying a function to that random variable. So it would be g of x. But we want to average it over the entire probability space. So what we do is, so we can represent that as an integration or a summation in the discrete case. So the expected value is, it's going to be this average value of g of x relative to your probability measure of your random variable. And this is, so when we are evaluating a loss function, usually what we have is we're going to be evaluating the expected value of the loss function relative to some random variable, to some input to the loss function. And that will give us, and when we're doing deep learning, we're trying to minimize this loss. So we're going to be trying to minimize the expected value of the average loss function. Let's see.
I think slide 46, I think, would be very helpful just for visualizations.
Which one's
and that's on conditional probabilities Bayes rule.
Oh, yes. Okay.
Yeah, and then also
Um,
maybe slide 43, random vector spaces with marginal probabilities, because that has some more details with
okay,
imagery. Yeah.
okay.
So I
So
would say maybe do those two. Yeah.
so random vector spaces. So for random variables, they map to the real line. But of course, we can map to, let's say, something larger than the real line, such as like an n-dimensional space like Rn. And also, if let's say you have a system and you're measuring somebody's, let's say, height and their weight, you could say the height is a random variable and a weight is a random variable. So you could say that the height is one dimension of your, and you could treat height as one dimension and weight as a different dimension. And all these variables that you're considering, you could consider it to be some ordered tuplet for a random vector space, which is basically an n-dimensional, an n-dimensional space. And yeah, so let me go over this quickly. So this has both pictures here. So this is important because, yes, so for random vector spaces, let's say you're evaluating somebody's height and their weight. Their height and weight might be correlated to each other. So your probability distribution isn't necessarily going to be an even distribution. You can't necessarily just multiply this whatever component of this distribution by whatever component of this whatever component of the y distribution with whatever component of the x distribution. It might be that only, even though only some of these probabilities, actually some of these ordered pairs occur, like short people will tend to have much lower weights than and people who weigh more might tend to be taller. So it might be concentrated along this sort of diagonal. So
how, can you find an example within deep learning that you can describe for Bayes' rule in conditional probabilities?
well, so the most important example is, or one of the most common examples is for conditional probabilities. If you're deep learning usually shies around, or usually tries to avoid Bayesian inference, but generative variational autoencoders in particular, they tend to, actually, no, this is a good example. Often you have your data distribution, and you also have your predictions as well. So using Bayesian inferences, using Bayes' rule, you're often trying to determine, if you have some observation, how likely is it that your model is correct? And similarly, if given your model, what's a probability that given certain parameters, what's a probability that you'll end up with a certain data output? And you'll be trying to maximize around it. I don't know if that's the greatest explanation.
Sure.
But
It just gives, yeah, it gives people some reference at least to deep learning, which is good. Yeah.
And actually, let me mention something quickly about information theory. So information theory was this somewhat interesting second half of chapter 3. So information theory, the basic problem is, well, one of the basic problems is how do you compare the distance between two probability distributions? And for information, it's this concept from physics called entropy. And entropy is defined as some function on the total number of configuration of states, which usually you represent as omega. And it turns out that in order to achieve certain properties, you want to use a logarithmic function to represent the entropy. You want to use a logarithmic function to calculate the entropy. And the total entropy of a system, the total entropy given a certain distribution is going to be the expected value of the log of the log value of the probabilities. So in physics, it'll be pi. For if you have a discrete number of outcomes, it'll be pi times natural log of p. And in information theory, they tend to use either base 2 or the natural log, and it'll be p times log p. And when we go into KL divergence, which is a way to create probability distribution distances, they actually use something very similar. So I have this definition of KL divergence here. So here, it's the KL divergence. It's going to be the log of the relative probabilities between the two distributions. So it'll be the KL distribution of PR to which K is a Boltzmann's constant. It's there. It's partially related to measurement, and it's also partially related to what base logarithm you use. You can change the base logarithm. You can change your logarithmic base by multiplying by a constant. So, but in information theory, in order to keep things simpler, and usually because you can change your you can scale your loss function by some multiple, you'll usually remove this constant. So for KL divergence, but getting back to KL divergence, they use a similar idea of entropy. So it's defined as log p divided by the probability of one distribution at a point divided by the probability of distribution at another point, and you multiply, and then you take the expected value relative to one of the distributions. And this is why it's not symmetric, because in order to evaluate the KL divergence, you're doing an expected value. So you have to choose one of the distributions to average it over. And if you were to change this to P of G, then it would be a different value. So that's why it's not a symmetric distribution. So why this is important is that oftentimes your loss function is going to be evaluating how close your probability distribution is created by your model to some other probability distribution. So it could be one example could be how close could be your classification probabilities. Like let's say you're trying to classify a bunch of images, and you have the probability, your data will provide the probability of classifying each particular image. Classifying each particular image to a specific label, but your model will have a different probability of classifying a specific image to a certain label. So in order to determine your loss function, you want to do something that will compare these two probability distributions, and the KL divergence is one such way of doing that. And there are other papers, or there are other distances or divergence measures which do the same thing. And one's called the Jensen-Shannon divergence. And that's, if you do generative adversarial networks, it turns out that their loss function is the Jensen-Shannon divergence. There's something called the Wasserstein-Earth mover metric. And actually, there's a paper that came out end of January, and which used this different distance metric for GANs, and it turned out to have much better properties. And actually, there's probably going to be a lot of interesting research or interesting papers done on those in the near future. And there's a total variation metric that I mentioned earlier, and there are a few other options as well. Okay.
Great. Well, I think that's probably about all we have time for this to go through the material. But you gave an amazing overview, really in depth, and super appreciated, Alex. I mean, really, 54 slides, that takes so much time and effort. But as we said, we're going to go ahead and share Alex's contact information. So if anyone has additional questions, or they would like, a more in-depth explanation on any aspect, he's already said he, would be happy to answer your questions. And then let's see. So I wanted to also let you guys know we're also hosting in-person meetups as well here in the Bay Area. So we are also going through the deep learning textbook in person. That's going to be Mondays bi-weekly, and you can find that on our meetup page. So that's meetup.com, and we're under Deep Learning Enthusiasts, and also you can find us under Deep Learning Textbook Study Group. We also host Thursday meetups where we've been going lately through Stanford CS231N on CNNs for computer vision. And we'll also be going over deep reinforcement learning soon because we've just finished up that series. So yeah, and if there's anything else that you want to learn on machine learning, deep learning, artificial intelligence, please just let us know and we will continue setting these up for everyone. And we do really appreciate, having our volunteers present. So if you would like to be a volunteer, it looks like we do need someone for the next chapter 4 on numerical computation. If you go to our meetup page on either of those groups, you can see the presenter sign-up form. If you want to sign up to volunteer for this online portion, just select the online tab. If you down at the bottom, if you want to sign up to do a presentation for the San Francisco in-person section, just select the in-person San Francisco tab and then sign up for that. We're going to start the first one this upcoming Monday, and we have Pankaj Kumar, who's going to be doing that one for us, intro in the introduction and the linear algebra chapters. And then, yeah, and we would love to have you join us. And again, so the goal for these meetups is just to learn together, right? No one, of course, is an expert on deep learning. Obviously, research is still coming out every day. This is very experimental. We're just trying to get as much information and learn as a community as possible. And just also as a reminder, these presentations can be as short as 10 minutes, as long as an hour or more as seen today. And just go in depth, as in depth in the material as you'd like to go. The goal is more just to share what you learned, right? And obviously Alex has a much more in-depth understanding of mathematics, so he was able to really dive deep with us today. The only thing we ask is please do not read directly from the book as your presentation. The goal is really to share what you learned, and also if you can include pictorial representations, that would of course help people that don't have as large of a background in mathematics. And if there are any other resources online, we would really appreciate that you share those as well. We'll be putting out more for everyone, both on the meetup page and on the Excel spreadsheet. So we really appreciate you guys joining us. And yeah, we'll be signing off. Thank you so much.
Okay, and and thank you for listening. Thank you for attending, and thanks to Laura for setting this up. And I guess a few final things to say on my end.
Sure.
First of all, those later slides, I guess they're not as well, to me, they're not as mathematically interesting as the earlier slides. They're basically interpreting these common concepts of probability theory, like expected value, marginal probabilities, conditional probability, but maybe from a more mathematical point of view. But if you understand them, then it should be fine. And the other thing is that so I started learning. I was a statistical consultant, and I started learning deep learning sort of in the spring of last year, and I had a lot of trouble reading some of these research papers because they kept throwing a lot of concepts around, which I didn't understand well enough that I was comfortable with. And actually, Ian Goodfellow's book, it's sometimes it can be hard to read, but it actually made me understand the material much, much better, because there are a lot of holes in my knowledge. And the problem is that a lot of the research papers tend to assume that you understand certain things because they have to be a certain length, so they tend to skimp a lot. But this book, it's actually a really good resource, and it provides a lot of information. In some cases, it's more detailed than some deep learning courses, like there's a Stanford deep learning course, and they mention a lot of ideas which are not included in some of those courses. So it's a fantastic resource, and like kudos to Ian Goodfellow for putting the time to put all of this together, because it's a pretty monumental undertaking. And if you want to learn about deep learning, it's an extremely good resource to carefully go through, but it just takes some time and commitment, especially the later chapters. But yeah, but thanks to everyone for attending, and hopefully it was somewhat interesting, and it gave some insight into probability theory, and maybe it might be helpful as a reference later if you were to read some of the more advanced research papers and you want to know what they're talking about. And I'll try to add in references later, some mathematical references later, so you can look up more information, although I don't know as many, I don't know as many like sources for this sort of things, because it tends to be more analytical, unfortunately. But I'll share what I know.
Wonderful. Thank you so much, Alex. We really appreciate your time. It looks like even some of the viewers say they will continue listening if you wanted to continue, but we do want to be respectful of everyone's time. So we're going to go ahead and go off for today. But thank you so much. You do have Alex's email now. It's alex.shim at gmail.com. That's SHIM is his last name. So please do reach out to him. If you want more information, he is happy, obviously, to share his time and his knowledge, and we really appreciate that. And thanks everyone for joining us today. This was super in depth and really great. So you're learning on a Saturday, learning deep learning. So thank you. We're going to sign off, and we'll see you soon.
Yep. Have a good one, everyone.
Bye.